An integrated programmable CPG with biped output. This paper is accepted for publishing in the IEEE transaction on automatic control. Cyclic motions are fundamental patterns in robotic applications, including leg robot locomotion and robotic manipulation and rehabilitation. Online trajectory generation for such motions represent challenging problems in robotics. In this work, we propose an architecture for the online generation of the reference joint trajectory for a robotic system out of a library of desired cyclic motions. The proposed architecture generates a smooth and natural reference joint trajectory that converges to the desired cyclic motion from any initial condition while preserving the position and velocity limits of the robot. This architecture is a safe and reliable tool for online motion modulation. The modern control architectures for generating cyclic motions consist of three main loops. First, the trajectory optimization designs the desired periodic joint trajectory resulting in the desired cyclic motion. Second, the online trajectory generation generates the reference joint trajectory converging to the desired one from any initial condition. And finally, the reference trajectory is followed by the instantaneous control of robot. Why do we need the online trajectory generation while we have the trajectory optimization loop? Well, the trajectory optimization is often complicated and computationally intensive, and thus it cannot respond to the robot or environment changes abruptly. In fact, the online trajectory generation follows three main objectives. First, smooth motion modulation, second, environment adaptation, and third, robot adaptation. Among the various methods have been presented for the online trajectory generation, central pattern generator or short-lived CPG has two main advantages. First, low computation complexity, and second, simple integration to the sensory feedback. Our proposed integrated programmable CPG consists of three main parts, two nonlinear mapping functions and one multidimensional programmable oscillator. This proposed architecture provides the global convergence of the reference joint trajectory to the desired one without any offline or online parameter tuning. It also provides both the trajectory and limit cycle tracking of the desired joint trajectory. It ensures the desired bounds on the reference joint trajectory and its first time derivative. Moreover, it generates a permanently synchronized reference trajectory. The present work extends our previous work about designing a programmable CPG for robotic applications. In the previous work, we presented a CPG consisting of a synchronized network of one-dimensional programmable oscillators. Instead, in the present work, we propose a CPG consisting of one multidimensional programmable oscillator. Our main idea for the multidimensional programmable oscillator is to use the trajectory tracking concept in the classical control. Considering the state space of a two-dimensional system in the trajectory tracking control, the system converges to an instantaneous target point. This point is a point on the desired trajectory that changes depending on the time. We developed the dynamical system with the same idea. However, we designed the instantaneous target point at each time instance as the closest point on the desired trajectory to the corresponding system states. For the position and velocity limit avoidance, we use the classical idea of the state transformation and we move from the bounded joint position and velocity space to the free space of new states. Thanks to the tangent hyperbolic function, if new states are stable, the position and velocity states are bounded. First experiment, passive arm rehabilitation with Kuka iiwa arm robot. In this experiment, we first generate offline a motion library for the desired nominal cyclic motions. The desired nominal motions have the time period of 10 seconds. For each motion, the corresponding desired periodic joint trajectory is generated by using parameter optimization technique. During the experiment, the physiotherapist chooses the desired nominal motion and the desired time period. For the desired nominal motion, we rate the desired nominal joint trajectory from the motion library. Then the desired trajectory generator converts the nominal trajectory to the desired trajectory where its time period is equal to the desired time period set by physiotherapist. The CPG generates the reference joint trajectory. And finally, the low-level servo control ensures that the reference trajectory is followed. The robot starts the motion from stop and then converts to the motion where the end effector moves on a horizontal circle in the Cartesian space. When the physiotherapist changes the desired time period or the desired nominal motion, the robot converts smoothly to the new desired motion. Second experiment, walking simulation of a 7-link biped. In this experiment, we again generate the motion library for the desired motions. For this purpose, we use the parameter optimization technique to generate a stable desired joint trajectory for a set of desired step lengths and step time. In the experiment, a high-level planner, which is a simple logic, chooses a set of desired step lengths and step type. We read the corresponding desired joint trajectory from the motion library, and then the CPG generates the reference joint trajectory. The reference joint trajectory is followed by the robot joint controller. In this experiment, a 7-link biped robot is simulated in MATLAB by using SimScape toolbar. The robot starts the motion from stop and converts to the desired walking gait. When the desired gait changes, the robot converts smoothly to the new one. At the end, the high-level planner gradually decreases the desired step length and increases the desired step time to stop the robot stably. Our future work includes first adding the sensory feedback into the CPG for adapting the reference trajectory to the environment and robot changes, and second, providing the capability of ensuring a desired constraint of the joint's trajectory. Thanks for watching this video. If you are interested in the details of this work, please check out our paper and code.